আমরা কি পড়ছিলাম? Characterization of materials. It may be a bulk material or it may be a nanomaterial. So in the characterization part, we are studying about the microscopes. We are studying about the microscopes. Uh, there are two types of microscopes: optical microscopes and electron microscopes. So we are studying the electron microscope, and in the previous class, we have studied the scanning electron microscope. That means the electron microscope that can scan the surface of a material. So what information we can get after scanning the surface of material? Actually, we can get information about the morphology of the substance. We can get information about various defects that are present in the surface of that substances, and the nature of the surface of the substance. This we can get this information. Actually, we can get from the scanning electron microscope, and sometimes we can get crystallographic nature also. Now, what is the difference between the electron microscope and the optical microscope? By optical microscope, we can directly see the object. That means we can directly see the image of the object, whether it may be real image or it can be a virtual image, but we can see the image of the object directly because optical microscope uses the light of the visible region. So if light of the visible region comes in our eyes, we can see the object. But by means of electron microscope, actually we cannot see the object directly. We cannot see the object directly. In case of electron microscope, electron interacts with the material. Electron interacts with the material, and the nature, and depending on the nature of the interaction, we can find some information. We can find some information of the material, and from that information, we can actually sketch a diagram or whatever it may be of that material. So there is a basic difference. We can see by optical microscope, but we cannot see by electron microscope. Second thing, by optical microscope or in the optical microscope, we use the wavelength of the visible light. So the wavelength of the visible light is much higher. It is about, say, for example, 250 or about 300 or 400 nanometer. But in the electron microscope, we use electrons. The electrons have particle nature and wave nature both. Electron have particle nature. You know about the dual nature of electron. The wavelength of electron is about 0.2 nanometer. Say for example, you want to write with a big marker. Then in a page, say for example, in this space, you can write say for example, if you want to write my name with a marker, it will require this much space. It is big. It is big. It is fattier. The written words are fattier. But if you want to write with this pen, or if you want to write with this pen, you see the tip is sharper. The tip is sharper. So we can write many things. We can write actually a sentence, a big sentence, not my name. You can write a big sentence with this pen. But if you use a marker, you can only write my name here. So what is the difference actually? Difference actually the in the tip. In the marker, the tip is broader, and in this pen, the tip is sharper. So the resolution of this pen will be higher than that of a marker. We will see the high resolution substance with this marker. We can write a high resolution substance with this marker. Now, if you imagine a wave of wavelength 250 nanometer and a wave of, say, for example, 0.2 nanometer, or a wave of 1 nanometer, and a scan with that wave, then you'll find that the scanning of wavelength 250 nanometer will be much broader. The resolution of the scanning of 1 nanometer wave or 0.2 nanometer wave will be more. The resolution will be more. You can scan, say for example, with that marker pen. You can, if you draw a line, it will be like that. But with this pen, if you draw a line, it will be one line like that. It will be one line like that. So resolution, you can draw 5 lines. You can draw 5 lines with this pen instead of 1 line with that marker. So resolution with this pen will be much higher. So the resolution with electron beam, the resolution, if you scan a substance with electron beam, and if you scan a substance with visible light, the resolution when you scan a substance with electron beam will be much higher than the visible light. And you will get much higher magnification with that electron beam. So here lies the difference between electron microscopy and your optical microscopy. So in the electron microscopy, the electron will interact with the material, and after interaction, the nature of the interaction will give us the information about the sample. But in optical microscope, we can see the sample directly. In electron microscope, we will get the information with much larger resolution, and we will get the magnification which is much higher than the electron microscope. but we cannot see a substance. Say, for example, we want to see a butterfly as a whole, a very beautiful butterfly as a whole. We can see it by an optical microscope, but we cannot see it by electron microscope. Secondly, we cannot see any colored substance by electron microscope. Think about it. In optical microscope, we shall see the color. We can see the color because we are seeing by our eyes. But in electron microscope, we are not seeing the object. We just see the result of the interaction of the sample with electron, and this result cannot be a color. Say for example, an electron strikes the outermost orbit of the electron of the sample, and the electrons will go out from the sample. You will see there is no color. This is a phenomena, and with this phenomena, we can gain an information about the, say for example, ionization potential of that atom. But you will not see any color here. But in optical microscope, as you have seen, as you can see the object as a whole, you can see the color. You can see that beautiful butterfly, but you cannot see it in the electron microscope. We can impart color on that electron microscope image later on to distinguish the picture. So you can impart color later on, but actually this is not the color of that surface. You have taken a surface. Say for example, this is a blue colored pen. You entered this subject. You entered this specimen in the electron microscope. You will not see the blue color of the surface. You will see how atoms are arranged, how molecules are arranged. Is there any cracks there? Is there in the surface, is there any bump? You'll see all that, but you will not see this color. But if you enter this in a microscope, you will see the color of this pen. These are the differences between an optical microscope and the electron microscope. So, so we are studying the scanning electron microscope. What is in the scanning electron microscope? First, you have to have a electron gun. What is the electron gun? The electron gun produces electron. How it can produce electron? In a tungsten filament, if you apply current, or if you apply voltage in a tungsten filament, it will emit electron. Or you can get electron by the field emission process. So so when you get electron from an electron gun, say for example, this is an electron gun. This is the tip. This is the tip of the gun by which electron will come out. Instead of ink, electron will come out, for example. Now, what will happen? The electron will come out and it will go in all directions, because electron will electron will repel each other. Electrons will repel each other. So when it comes out, it will go in all directions. So if I place an anode here, if I place an anode here, say for example, this cap is an anode. So what is anode? Anode is a positively charged substance. Anode is a positively substance. So when electron will come out from that tip, what anode will do? Anode will attract the electrons, and electrons will enter inside the anode. Now, what will be the nature of the attraction? Say, if you have say for it will depend on the voltage of the anode. If you have, say for example, if you use 500 volt, then it will attract the electrons with that much strength, 500 volt strength. If you use 20,000 electron volt here, then the energy, the pulling capacity of anode will be much, much higher. Then anode with 20,000 electron volt will pull the electron with much, much strength, which will increase the velocity of electron also. Can you understand this? It has, say for example, 500 electron volt. It will pull the electron. And if it has 20,000 electron volt, it will also pull the electron. But with 20,000 electron volt, this anode will pull the electron much harder, much stronger, with much strength rather. So if it pull the electrons with more strength, then the velocity of electron will be high. Then actually it will how much velocity, or with how much strength, or with how much voltage you use in the anode. It will depend on the nature of your experiment. But you can use from, say, 200 or 300 volt to 20,000 or 30,000 kilovolt, a very big span. Now, electron will come out from this, and it will go this way. This is an anode. So electron is now more or less streamlined. It is not discrete. Electron is not discrete. You see, there is a round tip here. So electron will go on that cap. So electron will have a definite shape. It is streamlined, and with this streamlined electron will go the first condenser lens. What it will do? It will make the electron streamline. You see, the electron is like that. There are many gases, so it will strict this. It will make it more tight. It will make it more tight. Now electron is coming more tightly, and there is a scanning coil. What a scanning coil will do? What a scanning coil can do? It can move the electron beam from here to here. Why it is required? It is required to scan it on a surface. If you want to scan something with this electron, you have to, what you have to do, you have to move this. Otherwise, you cannot scan. So a scanning coil will move the electron beam on the surface. If you want to write by this pen, you have to move the pen. Otherwise, you cannot write. So you cannot do a scanning without moving the electron beam. So the scanning coil will move the electron beam. Next one, what is next thing? The next thing is another condenser lens. What it will do? It will allow the electron to fall on a specific area of a substance. You want to scan in this point. So the lens will allow this electron beam to that point. So this is the construction. This is the construction of an SEM. I have shown you. And when the electron will fall on the specimen, mainly three things can occur. Electron will emit the secondary electron, or the electron that falls can be backscattered, and agar electron and agar your X-ray can be formed. These are the main things of an SEM. Now, let's come to the next section, next type of electron microscope, that is called transmission electron microscope. Now, what is that? It is also more or less same thing. From electron gun, electron will come out, and the anode will collect the electron, and it will go to the first condenser lens. You know, these lenses are all electromagnetic lens. These are not a glass lens. In the electron microscopy, the whole path of electron is highly vacuumed. Nothing will be in there, because if anything is in the whole path of electron will interact with that substance and it will scatter out. You will not get any beam. So you cannot use a glass lens here. They all are electromagnetic lenses. They all are electromagnetic lenses. So in transmission electron microscopy, what happens? From electron gun, electron will come out. Then it is your anode. Then electron will enter through the anode, and the first lens, electromagnetic lens, the electron beam will be tied there, and then object is placed. Here lies the difference between SEM and TEM. In SEM, from first electromagnetic lens, electron will come through a scanning coil, and then we have a lens, second electromagnetic lens, and then the electron beam will collide with the sample. But in transmission electron microscopy, the electron beam that comes out from the first electromagnetic lens, then object is placed then below the first electromagnetic lens. Now we are coming to the slide. Now you see, I'll come again to the first slide. You'll see here. This is the electron source. That means the electron gun. The electron gun from where electron will come out. Then it is the first condenser lens. First condenser lens. Then you can use the second condenser lens or not. It is actually the first condenser lens means the anode. The anode we are using to pull the electron. Then this is actual lens, the objective lens. From that lens, here lies the specimen. Here lies the specimen. This specimen must be very thin, very, very thin. So in TM, sample preparation is very difficult. It is because you have to have a very thin specimen. Why? Because we have to allow the electron to pass through the object or to pass through the sample. We have to allow the electron to pass through the sample. If it is thick, the electron cannot pass through the sample. So here is the thin specimen. Here is the thin specimen by which electron will pass through this. Now, it is a very thin specimen. Okay, electron will pass through this. That is also okay. But when it will pass through this thin specimen, it will interact the electrons or nucleuses of the specimen. Although it is very thin, but it will interact with the electron and nucleus of the specimen. But as the sample is very thin, it will not interact that much that it interacts with the in the SEM. It will interact somehow and it will pass through this way. So if, say, for example, this electron comes through this way, it will interact, say, for example, with an electron, and some you see you have a number of electrons in a beam. Say, for example, 4 electrons in a beam. 2 electrons will interact with the sample, and 2 of them will go directly passing through the sample. Then what will happen with that interaction? How it is interacting, how much sample is interacting, and how much sample is passing, how much your electron is passing through the sample without interacting. By knowing these things, we can have some information inside the specimen. So what is the difference between SEM and TM? In SEM, we shall see the surface morphology. In TM, we can see, or we will see the inside of an specimen, inside of the sample, how it is reacting with the with your how it is reacting the sample with the electrons. As because it is very thin, some of the electron will pass out, some of the electron will be diffracted, some of the electron will be backscattered. We shall not see the backscattered electron. We will not see the backscattered electron here, but we will see the passing electron. Our main thing is the outcoming electron. It comes from here. The electrons electrons will interact with the specimen. It may interact or it may not interact, and it will come down through this way, and we shall collect this remaining electrons, and from that collection of electrons we shall get some information how the inside of this atom, how's the inside of this atom. So you see here, this is the thin specimen. Electron will come out from this thin specimen, and and there is another lens here. It will focus the electrons in your screen, or you can get an image of that substances. So we shall see from the first slide. The transmission electron microscope is analogous to the slide projector. What is in the slide projector? How we can see in a projector in your classroom. You have a projector in your classroom. It is called multimedia projector. So a light is there. A light is there, and this is a lens. Here is the slide that is magnified. That means my slide here in my computer, it will go here. It will go here. Then electron will come, light will come on that slide, and through this way, it will be magnified by this way, and you will see it in the screen as magnified version. So this is the process of your slide projector or multimedia projector. In transmission electron microscopy, instead of using light, we are using the electron beam. This is the electron source. This is the anode, which collect the electrons, and this is the first condenser lens. It will go through this way. These are electrons, and a very thin sample is here, so that electron can pass through the sample, and during passing, it will interact with the sample, or it may not interact with the sample. Whatever it may be, it will go to the objective lens, and from this lens you will see in the screen, say for example, a screen of a computer. This is the aperture. Through this aperture, you will see the substance in a screen, in a computer screen, say for example. So this is analogous to the slide projector. Now, what will happen? In a conventional transmission electron microscope, A thin specimen is irradiated with an electron beam of uniform current density. A thin specimen is irradiated. A thin specimen, electrons are allowed to fall on a thin specimen. This is the electrons. Electrons are allowed to fall on a thin specimen, with uniform current density. Electrons are emitted from the electron gun and illuminate the specimen through a 2 or 3-stage condenser lens system. I told you about that. Objective lens provides the formation of either image or diffraction pattern of the specimen. You can have an image, or you can have a diffraction pattern. Diffraction pattern means this is a circular pattern or a hexagonal pattern of electrons. The electron intensity distribution behind the specimen is magnified with 3 or 4-stage lens system and viewed in the fluorescent screen. This is the simple transmission electron microscope. Here it is written. What will be the voltage of an instrument, and with this type of theory, which are the microscopy we can use. Now here, say for example, it is electron. The red one is the electron. It will pass through the lenses, and here is the specimen. It will pass through the specimen, and you'll see the figure here. You see, this is the line version actually of the transmission electron microscope from electron source. This is the condenser lens. That means the anode. This is the condenser lens. Here anode is there, and this is the object. Here is the object, and after object you will get objective lens, and you'll have another lens to increase the image size, and you'll find image here, or you can have a diffraction pattern here. Same thing is here. What is the difference between TEM and SEM? You will see the object is here, but in SEM, the object is down below. And these are the image forming system. You know how image can be formed. I have shown you this is the objective lens. From electron comes through the objective lens and forms the image. Now, why TMS used? You will find actually this type of structure. You will find by TM this type of structure. These all are the molecules, or you can find atomic scale also. You can say bismuth titanium oxide. One is bismuth atom, one is titanium atom, another one is oxygen atom. Say, for example, the black ones are oxygen atom. You can find this a substance in atomic scale. The uniqueness of TEM is the ability to obtain full morphological, that means grain size, grain boundary, interface, secondary phase and distribution, defects, crystallographic, atomic, structural, and microanalytical, such as chemical composition in nanometer scale. So in TEM or by TEM, you can have a resolution to the atomic scale, but the limitation is in sample preparation. It should be very, very thin. The sample should be very, very thin. So a very, very thin sample preparation is not a easy matter. It requires a very very heavy training to prepare a TEM sample. So otherwise electron will not pass through the sample and will not gather any information, or you will be misinformed rather. So this is the limitation of TEM. And comparison of optical microscope, transmission electron microscope, and SEM. I told you all these things. Now we have another kind of microscopy, which is scanning tunneling microscopy. Okay, I can show you two video first for TEM and SEM. দেখা যাচ্ছে? দেখা যাচ্ছে কি?
না স্যার।
জি স্যার।
হ্যাঁ, দেখা যাচ্ছে না? না, কি বলো, দেখতে পাচ্ছ না পাচ্ছ না?
না স্যার, দেখা যাচ্ছে না স্যার।
দেখা যাচ্ছে না।
আচ্ছা, তাহলে আমাকে কি করতে হবে? আমাকে শেয়ারিংটা বন্ধ করতে হবে না ফার্স্ট? এবার
ইয়েস স্যার।
এটা একটা SCM। শব্দ শুনছ?
ইয়েস স্যার।
কি হলো? দেখো এখানে থিন অ্যান্ড টাইট, দেখো এগুলো, এই যে এগুলো থিন অ্যান্ড টাইট হয়ে যাচ্ছে। সেকেন্ডারি ইলেকট্রনস ডিটেক্টর, ব্যাকস্ক্যাটার্ড ইলেকট্রন ডিটেক্টর, এটা হচ্ছে সেকেন্ডারি ইলেকট্রন ডিটেক্টর। দিস রেড ইলেকট্রনস আর দ্য সেকেন্ডারি ইলেকট্রনস, so these are the secondary electron detectors. It can be a backscattered electron detector or X-ray detector, whatever it may be. You'll see the top view here and the detector view here. This is the top view. These are the backscattered electrons. Yes. This is how agar electron or X-ray photon occurs. You'll see some X-ray photons here. You'll see some X-ray photons here. Here is the X-ray photons. This is the X-ray photon. তোমরা কি আবার দেখতে চাও না দেখেছো ভালো করে? হ্যাঁ, দেখেছো কে ভালো করে না আবার দেখতে চাও? কেউ কি শুনছো আমার কথা?
স্যার ইমেজিং থেকে আবার দিলে ভালো হতো।
পুরাটাই আবার দেই। এটা সাউন্ডটা কেন জানি আবার আসে নাই। এটা ব্যাকস্ক্যাটার্ড ইলেকট্রন ডিটেক্টর আছে, এনার্জি ডিসপারসিভ এক্স-রে স্পেকট্রোস্কোপি ডিটেক্টর আছে, সেকেন্ডারি ইলেকট্রন ডিটেক্টর আছে, তিনটা ডিটেক্টর আছে। এটা হচ্ছে সেকেন্ডারি ইলেকট্রন ইমেজিং। নাও ব্যাকস্ক্যাটার্ড ইলেকট্রন ইমেজিং। এবার আসো এনার্জি ডিসপারসিভ এক্স-রে স্পেকট্রোস্কোপি, এটা আমরা একটু পরে পড়াবো, যেটা তোমার এক্স-রে ফোটন ইমেজিং। এখানে দেখবে এরকম জিনিস বের হচ্ছে। এটা অগার ইলেকট্রন কেন? ইনার শেল থেকে এটা হয়। দেখো এখানে কপারের ইনার শেল থেকে একটা ইলেকট্রন বের হয়ে যাচ্ছে, আউটার শেল থেকে একটা ইলেকট্রন ইনার শেলে আসছে, আউটার শেল থেকে একটা ইলেকট্রন ইনার শেলে আসছে, এবং এখান থেকে এক্স-রেটা বের হয়ে যাচ্ছে। কেন? আউটার শেলে এনার্জি বেশি, ইনার শেলে এনার্জি কম, এক্স-রেটা বের হয়ে আসছে। নাও এটা গেল। আবার যাই, টিএম দেখা যাচ্ছে
না স্যার।
এটা নিয়ে বড় সমস্যা আছে, আগে তো এরকম হতো না। এখন দেখছো? এখন দেখছো?
না
না
স্যার।
স্যার।
কি করতাম বলো তো? এবার দেখছো?
ইয়েস স্যার।
ধন্যবাদ দিলাম। This is the TM. And the next one is scanning tunneling microscopy. Scanning tunneling microscopy. So some tunneling is there. From the name of this type of microscopy, some tunneling is there. What is that tunneling? Say, for example, there is a bulb here. If there is a bulb here, and to bring this bulb from here to here, what you have to do, you have to climb up this barrier and go here, and it will come here. This is the classical mechanics or classical view of classical mechanics. What you have to do, you have to you have a bulb here, it will climb up through this barrier and it will come here. But according to quantum mechanics, this can also tunnel through this barrier. I have teached you in the nuclear chemistry class that tunneling effect, the nuclear particles, the protons or neutrons can tunnel through the barrier. So, according to quantum mechanics, uh, uh, actually, what you have to do, you have to have some energy to climb up this barrier and go here. But but according to quantum mechanics, you do not have that much. If you do not have that much of energy, then you can tunnel through this barrier. You can tunnel through this barrier. You can tunnel through this barrier in this portion, or in this portion, or in this portion, whatever uh, whatever the energy permits. But you can tunnel through this barrier. This is the main principle of uh, mm, tunneling. Tunneling. So, what is the tunneling current? In a metal, the energy level of the electrons are filled up to a particular energy known as Fermi energy. Actually, in a metal, you see, if you consider a metal, the metals have electrons. Say, for example, this is made of a metal. For example, this is made of a metal, or the tip of the pen is made of a metal. So it the tip of the pen consists of many metal atoms, which is made of protons and nucleus and electrons. So the electrons are inside the metal, a metal atom. It will not go out from the metal moiety. Now, now, say for example, this is another particle. Now, if it is very close, say for example, it is here. Now, electron will not come out from the metal, that means from the tip to here, or from here, electrons will not go to the tip. Why? Because some energy barrier. What is the energy? The nucleus. The nucleus is pulling the electrons. So if you want that electron will come out, then you have to give energy to the atom. Then if it is greater than the ionization energy, then the electron will come out. This is the barrier. You have to give energy to the electron to come out from the atom. This is called barrier. Now, sometimes what happens, you did not, or you do not give any energy, but electrons will come out. That is the tunneling. You have a barrier here. You have a barrier from passing electron from one item to another item, or from here to here. You have a barrier. What is that barrier? Energy barrier. Energy barrier. Electron. You have to give energy to the atom to lose out the electron, and to go in another specimen. But if you bring this tip very close to the specimen, or to some body, then electron can move to that body. Electron can move from this body to that body without having any energy. Electron is in the atom of metal, but when other atom is very close to the atom, then electron will go from this atom to that atom without having any energy. That is called tunneling, without having any energy. You see that Normally it have to pass the barrier, but if two specimens are very close to each other, then the electrons will tunnel from one atom to another atom if both the atoms are conductors. If both the atoms are conductors, if one is conductor, one is non-conductor, this tunneling effect will not happen. So what is the tunneling effect? Electron can tunnel from one atom to the another atom of another specimen when they are very close to each other, and the second condition is the tip is very sharp. So the electrons need to overcome a barrier to travel from a tip of a specimen or vice versa. When a sharp metallic tip is brought very close to the surface of a conductor, when a sharp metallic tip, say for example, this is a sharp metallic tip and this is a conductor, then if I bring this very close to the conductor, then what will happen? An electric current can be detected due to the tunneling of electron through the air gap. If I keep this very close to one another, then electron will come out from this surface to the metallic tip and you will find an electric current. In this case, air gap is considered as the barrier and is only a few angstrom thick. When an applied voltage V is applied between sample and tip, this tunneling phenomena results in an electrical current called tunneling current. If you apply some voltage here, then you will get an electrical current called tunneling current. You see, this is the tip. This is very sharp tip made of atoms, and this is the sample. If you bring this tip very close to each other, electrons from the sample will go to the metallic tip. Electron from the sample will go to the metallic tip and you will find a current. If you apply some voltage here, you will find a current. By measuring this current, we can see the surface of the we can have the information of the surface of the sample. So how we see it? So what is the components of STM, scanning tunneling microscope? First component is the scanning tip. It is it is a very sharp tip made of tungsten metal or platinum iridium alloy, where at the every end of the tip there is one atom of the material. Here you will find the tip is so sharp that tip is so very sharp that you will find only one atom of the metal at the end of the tip. So when you can make this condition fulfill, then scanning tunneling then tunneling will happen. You have a tip with only one atom at the very end of the tip. Now, second thing, you have a piezoelectric scanner. Piezoelectric called. What is a piezoelectric scanner? This is the scanner. This is the tip, and the tip is attached to then scanner. What is a piezoelectric scanner? Piezoelectric crystal expand and contract very slightly depending on the voltage applied to them. This is a crystal, piezoelectric crystal. Its property is that if you apply some voltage, it can contract or expand very slightly. It can contract, very slightly, or it can expand very slightly. It is the property of piezoelectric substance. So a piezoelectric substance is attached to the tip, and the piezoelectric substance is such that it can contract or expand when you apply external voltage. And two more things. One is a scanning unit and data processing unit. It is normal thing. So we require the two things. One is tip and another one is piezoelectric tube. This is the main thing of an STM. Now, one vibration isolation system, that all are detectors actually. So what will happen? You see, this is a piezoelectric substance, piezoelectric scanner, and this is the tip, and this is the sample. You see, the tip is so sharp that there is only one atom at the end. Now, if it comes very close to the sample, this is the sample. If tip comes very close to the sample, you will find a current here. You'll find a current here, and by measuring that current, you can have information about the surface morphology, how it comes. You see, working of STM. First, a voltage bias is applied to the tip, is brought close to the sample by coarse sample to tip control. So first bring the tip very close to the sample. Now, if you apply some voltage, voltage bias will cause electrons to tunnel between the tip and the sample. So if you apply some voltage, then electron will pass from the sample, electron will cause electron to tunnel between tip and sample, creating a current, and the current will be measured. Now, how it is measured or how you can do it, you see here. Say, for example, this is a sample with uneven morphology. You have a sample with uneven morphology. Now, this is the tip. So, say, for example, the tip will pass like that. The tip will move like that. So, here you will get the current. Here distance is less, you will get a current. But when tip comes here, say for example, tip comes in this position. Now see, the distance between tip and the sample is then higher. Then you will not get that much of current. But when tip will come here, you will again find some current. Now, if tip comes here, you will again find some current, but not that much of current. But if tip comes here, will distances becomes larger. So the tip will move with a constant height. You see, the tip will move with a constant height, and the current will be more or less depending on the surface morphology. This is called a constant height method. you have you have kept the tip at a constant height in this height, and the current then may be more or less depending on the morphology of the substance. Now this is one method, constant height method. Another is constant current method. What is that? The current should be constant. Now, to make the current constant, what you have to do, say for that, the current is constant. Say, for example, the current is 5. So, when the current will be 5, at this distance, the current will be 5. Now, if this tip comes here, the current will not be 5 because this distance is larger. So, to make the current constant, the tip will go down here to make the distance constant. If you will get constant current if the distance is constant. Otherwise, you will not get constant current. So the tip will come here. The tip will come here to make the distance constant and to make the current constant. So here tip will move. Here the tip will move up and down. Here the tip will move up and down depending on the morphology of the substance. So in the previous one, the height of the tip is constant. You will get the current, varying current. You will get the varying current. But here, the height of the tip is not constant. The current is constant. So the height of the tip will it will up and down because you have to keep the distance, always the tip sample distance constant. You have to keep the sample tip distance constant. To make it constant, the tip will move up or down, depending on the morphology of the substance. So from that current or from that up and down of the tip, we can say, or have an image about the morphology of the substance. So STMES are not direct surface images of the sample as in the case of optical microscopy. Rather than it is a measure of local density of states of material as its surface of the function of XY position. You'll find this type of thing. You'll find this type of thing. You'll find actually this type of thing in the your spectroscopy or STM your microscopy. Here you see the surface goes up and it remains constant here and it will go down here. You can have this type of image also. The surface will go up and down. So we can see the surface morphology. We can see the surface morphology of by STM. There are some merits and demerits of STM. The advantages are STM is versatile. It can be used in ultra high vacuum, air and water, other liquids and gases. These are the advantages, and it is very expensive. These are the disadvantages. You can understand it if you read it. So there is nothing to tell. So this is an STM instrument. There are different parts of an STM instruments, and you see here, this is the surface and this is the tip, and you'll see the surface tip electron tunneling when it comes at a very small distance. Now, next one is energy dispersive X-ray analysis. I told you about energy dispersive X-ray analysis. It is called EDX. EDX. What is that X-ray? What is that X-ray? If you have an atom. Now you have in that atom you have electrons in outer shell and in the inner shell. Now, if an electron from the inner shell goes out by any means, by bombarding with another electron, if an electron from the inner shell goes out, then electron from the outer shell comes to fill up the space. Then the electron in the outer shell obviously have high energy than the inner shell, so it will lose some energy when it will go to the inner shell, and this energy, it will lose this energy by the form of X-ray. This X-ray is characteristic of an element. That means if it is copper, then you will find X-ray of a definite wavelength. If it is nickel, you will find X-ray of another wavelength. So if you can detect the X-ray and its wavelength, then you can tell that which this X-ray comes from which element. These X-rays are always characteristic. So if this is the energy dispersive X-rays, X-ray peak, you can detect the X-ray. If you detect the X-ray, you can tell that this is this element, this is this element, this is this element. So how it is detected? I have told you that if it goes, if electron goes out from this level, then electron will come from here to here, or if an electron goes out from this level, it can come from here to here, from here to here, or from here to here. Depending on this transition, a characteristic X-ray will go out, and by measuring this characteristic X-ray, you have seen in the SEM that X-ray is measured by a detector. By measuring that X-ray, we can tell the concentration of that element and name that element. Say, for example, a substance has 3 or 4 elements. We can tell the names of that elements. It is sulfur, or it is silicon, or it is magnesium, and the concentration of that elements. You see, this is the concentration. The concentration is sulfur is higher than that of oxygen or silver. This is the EDX. So these are the important EDX parameter. That means what will be the voltage, what should be the voltage of electron, what should be the current rate of the electrons. Is there will be a dead time, what should be the angle. These are some parameters, but the main theory lies here, the EDX. So these are the microscopic part. And another thing, Please see the syllabus. Is there anything left? কিছু বাকি আছে, দেখো ভালো করে। সবই পড়ানো হয়েছে? সিএম, টিএম, এসটিএম, ইডেক্স, কম্পারিজন। আরেকটা জিনিস তোমাদেরকে একটুখানি পড়েছিলাম, সেটা হচ্ছে এএফএম। যখন আমি লিথোগ্রাফি পড়িয়েছিলাম তখন এএফএম, এটাও একটু খুব দরকারি জিনিস। যেহেতু তোমাদের সিলেবাসে নাই সেহেতু আমি পড়াচ্ছি না বেশি করে, কিন্তু তখন তোমাদেরকে আমি পড়িয়ে দিয়েছিলাম। সো এএফএমটাও কিন্তু তোমাদের খুব দরকার আর কি।